Hello everyone. In this video we're going to start to give definitions for what are called bounds. So we're going to look at upper bounds and lower bounds, and this is all for some subset of the real numbers. Now we'll also talk about the greatest lower bound and the least upper bound, or maybe we'll use their other names, which are going to be the infima or infimum and the supremum. So let's start simply, right? So we'll give a nice definition here for what we mean by a bounded set. Okay, and well, we'll actually have some a little more subtlety in it at first, but we'll at least finish this definition by saying what it means for a set to be bounded. So let's say we have some subset of the real numbers. Okay, we'll call this subset, say, A. All right, so we're going to say that A is bounded from above. So bounded from above. This is very conventional language. I also like to use a different phrase, or upper bounded, which makes just as much sense. It's not quite as commonly used, but I think it will make sense here. So we're going to say that it is bounded from above, or upper bounded, by some number u. Okay, so some real number u. If, so what does that mean? If for every element in the set, we have that element is no bigger than capital U. Okay, so that's all we mean. Your set is bounded if there's something which is bigger or at least greater than or equal to everything in your set. Okay. So from a pictorial point of view, if I draw my A, and it might not, be just one interval, could be a whole bunch of stuff. There has to be some number U such that you do not have any of this green to the right of the U. Okay, so that's what we mean when we say that A is upper bounded or bounded from above. And in this case, we're going to call U an upper bound for A. Okay. Now, what is at least pretty clear in this picture is that while U is an upper bound, if I drew in this capital V, that would also be an upper bound. And you might say, well, that's kind of a better upper bound, right? Because it's somehow smaller than the U, but it's still an upper bound, right? It's getting you closer to where the set A actually is. So we're going to come back to that notion, okay, of looking for better upper bounds in just a little bit. Now, it could be that A is not bounded from above, right? So it might be that these little green highlighted areas just keep going on and on to the right, in which case, so if A is not upper bounded or bounded from above, then we're going to say that A is unbounded from above. Is unbounded from above. Or, of course, there must be some sort of corresponding statement here. We could say A is upper unbounded. Okay. Everything we just said for an upper bound, right? There should be some analog for lower bounds. All right. So it's not hard to translate all of this stuff, right? We would say, okay, A is bounded from below, or lower bounded. Okay, so that'll be the corresponding language, lower bounded. Okay, by some number, let's call it L for lower, right? So some real number L if, okay, look, we're just copying now. For every element A and A, we have, well, it should be that this little a is not less than or equal to the L, but actually should be greater than or equal to, right? L should be this lower bound now, right? It should be smaller. So in this picture, if I extend just a little bit more, I could pick some spot over here. Okay, so if again these green bars represent the A, then this L is an upper bound for the set A. Okay, and of course we can continue on here and say if A is not lower bounded, then A is unbounded from below. Or lower bounded, lower unbounded, excuse me. Okay, now in this picture, the set A that we've drawn with these green bars, we can see it has both an upper bound and a lower bound. And in that case, we're just going to say A is bounded. Right? So you ever hear that phrase, A is bounded, then we're meaning it is bounded from above and from below. So if A is upper and lower bounded, then we say that A is bounded. And in the case where neither of those is true, so if A can just keep on going up and up and up and also down and down and down, then we're going to say that A is unbounded. Right? So if A is upper and lower unbounded, okay, we'll just copy here, then A is unbounded. Cool. So let's do a couple examples here. So what if I take the interval 1 to 3? So the interval 1 to 3, which on a real number line, say, okay, there's 1, there's 3. I'm not including 1 or 3, right? I'm using the parentheses. So this is upper bounded by 7. Okay, so I could extend this line quite a bit here, and I say, look, there's a 7. Nothing in the interval between 1 and 3 is bigger than 7, right? 7 is at least as big as everything in that interval. Of course, it's also upper bounded by 5. Yeah, so 5 is sitting in there. Nothing in the interval is bigger than 5. Right? It's also upper bounded by 3 itself. All right? Nothing in the interval is greater than 3. In fact, nothing in the interval is equal to 3. Notice I have this parenthesis, so the 3 is not included. Okay, so actually, right, I can do there. This is upper bounded also by 3. Okay, it's lower bounded by, well, I can go over here and I can put it like a -2. It's also lower bounded by 0. Yeah, another possibility. It's also lower bounded by 1 itself. Right? Nothing in that interval is smaller than 1. So I have lots of different possibilities for upper and lower bounds. These are not unique. Okay, let's try a non-example of boundedness. Well, if I'm looking for an upper bound, actually, that's okay. All right, so I'll draw my little picture here. Okay, maybe 4 is over here, and it is a square bracket, which means I get to include 4 in the set. But I'm going from -infinity to 4. So it means I just have everything. Okay, it just goes on and on and on. So it is upper bounded. So it is upper bounded by, well, you can pick whatever ones you want now, right? Like it could be by 1,000 or 18 or even 4, all right? And you might say, well, doesn't everything in the set have to be smaller than the upper bound? And no, it's not quite, right? When you're upper bounded, you just need your upper bound to be greater than or equal, right? Equal is okay. So you can have an upper bound in your set. That's fine. So 4 is an upper bound for this interval negative infinity to 4. Okay, but on the left-hand side, I'm looking for a lower bound, and there isn't one. All right, this just keeps going as far as you want. Negative infinity is not a real number, so I can't use that as a lower bound. And if I picked any really tiny number, negative a billion, well, this gets smaller than that, right? Negative 2 billion is in this set. So this is lower unbounded. So not every set is going to be bounded. Not every set that has an upper bound will have a lower bound, right? And of course, you could have neither. But in the real numbers, right, if you're looking for an interval, maybe it looks something like that. So this is unbounded. But it's not the only unbounded, right? I don't necessarily have to have all the real numbers to have an unbounded set. In fact, let's just draw a picture of something. So let's say I have 0, and I'm going to do 1/2 to 3/2, and then 5/2 to 7/2, and then 9/2 to 11/2. And I'll go the other way over here, right? So I'll have a negative 1/2, and negative 3/2, and a negative 5/2, and a negative 7/2. And I put these all together, right? And they're going to keep going forever and ever. Okay, so on and on and on in both directions. So I don't contain all of the real numbers, but it's definitely unbounded, right? In both directions, I can just get as large as I like or as small as I like, large, negative, whatever you want to call it. Okay, so these are some examples of bounded sets. Now, we've mentioned here a couple times, right? Just because you have an upper bound, it doesn't mean that you have a unique one. In fact, look at that. There you do not have unique upper bounds. However, we would like to single one of them out, right, as the best of all the upper bounds. And there's a very good case to be made in, say, this picture here, that the 3 is the best of the upper bounds. It's somehow the most efficient. If somebody wanted to know how big this set 1 to 3 can get, and you told them 1,000,000, and they say it can get up to 1,000,000, well, no, it can't get up to 1,000,000, right? You say it can never go above 1,000,000. Well, that's not nearly as useful as telling them, right, well, it can't get above 3. Okay? So we want to write down some language that's going to talk about not just an upper bound, but the smallest of all of them, what we're going to call the least upper bound, okay, or the supremum. So let's get to our next definition. So again, we let A be a subset of the real numbers. So if A is upper bounded, okay, so we know from the start that there is some upper bound, then a real number U is called a least upper bound. It's called a least upper bound. Or a supremum. Okay, and this is actually the word we're going to use more frequently. So a least upper bound or a supremum for A. If, well, first, U is an upper bound. So if U is an upper bound for A, and if whenever capital U is an upper bound for A, we have that little u is less than or equal to big U. Okay, so of all of the upper bounds, little u is the smallest of them. Okay, and I showed you once how we translate everything for upper into lower, so I don't want to go through all of this sentence. Just you don't have to waste your time watching me write it. Okay, but we can translate all of this into language where now we're looking for lower bounds. And so I'll just say we similarly define, well, if we're looking at all of the lower bounds, then we kind of want the biggest one, right? That'll be the most efficient. So we're going to call that actually a greatest lower bound. Or, and the word we'll use more frequently is infimum. So you have the supremum and the infimum for A. Okay, so let's do a couple examples here. So if I take the interval 1, 3, then of all of the upper bounds, 3 is the smallest one. So this has supremum 3. And of all of the lower bounds, 1 is the largest of them. So this has infimum 1. All right. Now, I said here, like, 1 is the greatest lower bound. All right. And we're actually going to write down a theorem in just a moment that says it really makes sense to talk about the supremum, the infimum. Before we do that, we'll just do one last non-example here. So if I take the interval 1 to infinity, well, this has no upper bound, right? It goes all the way to infinity. So because it has no upper bound, it can't have a supremum, because the supremum should be the smallest of all the upper bounds, and there is no upper bound. So this has no supremum. But it does have an infimum, right? 1 is still the greatest of all the lower bounds. So it has no supremum, but the infimum is 1. Okay, so the last part of the video here is going to be this theorem that says that if you do have a supremum and you do have an infimum, right, or you have an infimum, then they are unique. All right, so that's actually our name here. So suprema. So by the way, right, the plural of supremum is suprema, and the plural of infimum is infima. So suprema and infima are unique, which is kind of a funny statement because you're looking at a plural and then saying there's only one of them. All right, so here's our theorem. Let's say you take some subset of the real numbers. And first, we'll just consider if it's upper bounded. So if A is upper bounded, right, but there'll be a similar statement. We'll just write respectively lower bounded. Then it has a unique supremum, respectively infimum. Okay, so you cannot have two different numbers that you say, okay, both of these are least upper bounds for the set. Okay, so if I say I talk about the supremum and you find the supremum, we're talking about the same number. Okay, so let's do a proof of that. And I'll just prove it for the suprema, but the same proof essentially will work for infima. So we assume, well, it's already assumed that A is upper bounded. So let's assume we have two upper bounds, right? In fact, not just upper bounds, but least upper bounds, right? We have two suprema. So assume U and U prime are both suprema for A. Okay. Well, in that case, we know since U prime is a suprema, it is the smallest of all lower bounds, right? It is, or that is, really, it's less than or equal to any other lower bound. So, well, U, or upper bound, excuse me, U is an upper bound, right? All right, our assumption was that if you had some sort of a supremum and you had some other upper bound, then your supremum had to be less than or equal to that upper bound, right? Well, U prime is a supremum. U is an upper bound. Therefore, U prime is less than or equal to little u. On the other hand, U itself is a supremum, and U prime is an upper bound. Therefore, by the definition of supremum, U is less than or equal to U prime. And hey, when you have an expression like this, all right, a chain of inequalities where the beginning and the end are equal to each other, this implies that they're all equal. So thus, U is equal to U prime. Okay, so a similar proof holds for infima. Okay. All right, so stay tuned for another video where we look at sort of the opposite, or rather dual thing where you look for in math whenever you know that some concept is unique. Well, it's also good to ask, well, does it exist? So when we talk about existence of suprema and infima, we're going to need actually a new axiom, something called the axiom of completeness. And we'll talk about that in another video.